Hi everyone, welcome to my talk about contextualized emotion recognition in conversation as sequence tagging. I'm Yan Wang from Ping An Technology, doing research about natural language processing. Today's topic is about emotion recognition in conversation. Emotion recognition in conversation, or simply called ERC, is an emerging topic in NLP technologies, but it has been attracting more and more researchers' attention due to its great potential in many scenarios of real-world applications. For example, a healthcare bot may understand the user's emotion so that it can be more empathetic, generate some effective responses to comfort patients. For a call center, emotion recognition based on spoken text data can make real-time determination of users' mood swings and assist agents adopting optimal coping strategies. ERC technology can also be used for offline customer service quality inspection to annotate emotion tags of both agents and customers. This requirement is very common in insurance industry. The problem definition of emotion recognition in conversation is quite simple. Given the conversation, including M participants and constituent utterances, predict emotions labels for each utterance. However, compared with its simple definition, it faces two much more difficult challenges. For example, how to model the long-range context dependencies of utterances, how to check emotional states for each speaker in a multi-party conversation, how to model the presence of emotion shift and inertia for speakers. Previous works have pointed out participants in a conversation have emotion inertia, so their current emotional state depends a lot on their previous states. Inspired by this, we want to know whether emotional tags of the conversation have the similar inertia. That means emotion tags depend on each other. According to our observation, in a conversation, similar emotions tend to appear adjacently, while dissimilar emotions seldom appear in neighborhood. We call this phenomenon emotional consistency. It reflects the inertia of emotional tags of the conversation. For example, if the emotion of current utterance is happy, the tag of next utterance tends to be happy, excited, or neutral rather than sad, angry, or frustrated. This pattern also applies to other emotions. So we can review ERC task from a new angle. In previous works, they just predict emotion tags for each utterance based on contextualized representations without explicitly modeling the relationship between tags. Instead, for the first time, we treat ERC as sequence tagging, which consider relations between nearby emotion tags and choose the globally best tag sequence for the entire conversation at once. Based on this idea, we propose CESTA. It is the abbreviation of Contextualized Emotion Sequence Tagging. Now, let's take an overview of CESTA. For each utterance in a conversation, it employs a single-layer CNN to extract the textual feature and fed it into the global and individual context encoders. In fact, we may achieve better results if we choose other model as the utterance encoder, such as Elmo, BERT, and GPT. We use CNN as the text encoder just because some existing works on ERC also use CNN, and we want to conduct a fair comparison with them. Obviously, participants in a conversation have influence on each other. This is the so-called interspeaker dependencies. Counterparts can lead to a change to the current speaker's emotional state. In other words, when classifying one utterance, other utterances in the conversation provide important contextual information. So we need a global context encoder to model these dependencies. LSTM and the transformers are two most common models for learning the context information. However, both of them have shortcomings. LSTM can capture the fine-grained sequential context Compared with the original RNNs, it boosts a bit the dependency range they can run due to the carefully designed cell. But the influence of distant context can also be lost. This problem is inherently related to its recursion structure. For some conversation datasets containing many long conversations, such as IEMOCAP, LSTM may not be a good choice. The transformer can model long-range dependencies quite well due to the self-attention mechanism. However, the positional encoding in the transformer only provides vague relative position information, forcing the layers to re-event trigonometry at each layer for specific sentence success. So, intuitively, how about combining them together? In the paper about the transformer-based language model last year, adding LSTM layer on transformer blocks produced good results. Here, we use a similar method, that is, use the transformer blocks to enhance LSTM. Specifically, the enhanced context encoder takes textual features of the utterances as input, applies a multi-head self-attention over them, followed by point-wise fully connected feed-forward layers to produce contextualized representations. Then, these representations are fed into a bi-LSTM to produce the global context encodings. Now, let's consider self-dependencies of speakers in a conversation. As mentioned before, speakers have emotional inertia, so their current emotional states are influenced by previous states of their own. We implement an LSTM as the individual context encoder to output all speaker states for each time step. It exploits the current input utterance to update states only for the corresponding speaker. There is no need to use transformer to enhance the LSTM because in most conversations for each speaker, their self-dependencies are relatively short. We even don't use bi-LSTM here because LSTM is good enough. Maybe bi-LSTM is better. We'll conduct some experiments to check it out. Inspired by the emotional consistency of conversations, we consider ERC as a task of sequence tagging, which is beneficial to consider the correlations of nearby tags and choose the globally best chain of tags for a given input sequence. For this reason, a CRF is employed in SESTA to yield final predictions with the aid of neighboring tags. The concatenation of the global and individual context encodings are fed into the CRF layer to jointly model the probability of the entire sequence of tags to capture dependencies between adjacent tags. Here are some experimental settings. For ease of comparison with state-of-the-art methods, we evaluate SESTA on 3 artificial conversation datasets: IEMOCAP, MELD, and Daily Dialogue. Compared with state-of-the-art methods, we obtain considerable improvements on IEMOCAP and Daily Dialogue, and marginal improvement on MELD dataset. For the former two datasets, our SESTA performs quite well because it incorporates as much information of emotional dynamics as possible. For MELD dataset, utterances suffer a shortage of emotion-specific expressions. Additionally, there are many conversations containing more than 5 speakers. This nature imposes great difficulty for our model. We evaluate the effect of transformer enhancing on conversations with different lengths. On the test dataset of IEMOCAP, conversations are grouped by length and fed into 2 models. One is our SESTA with a transformer-enhanced global context encoder. Another is a contrast model that only uses LSTM-based global context encoder. It is easy to observe that both context encoders have similar effects on relatively short conversations. However, the advantage of transformer enhancing are more obvious as the length of conversation exceeds 54. This confirms the contribution of transformer to the modeling of long-range contextual information. This time, we remove the CRF layer from SESTA. For most emotion tags, SESTA demonstrates a more obvious emotional consistency. That is, the same tag are more likely appear adjacently in given conversations. For the tag of angry and excited, SESTA reflects less emotional consistency than the contrast model. However, we find that the quantitative distribution of next tags of angry and excited given by SESTA is closer to the ground truth than the contrast model. This phenomenon is worth to further study. Here are conclusions and future work. Based on the contextualized utterance representations, SESTA leveraged past and future emotion tags to jointly decode the best tag sequence for the entire conversation at once, modeling the emotional consistency via CIF and enhancing the context encoder via the transformer are beneficial to our model. SESTA achieves new state-of-the-art results. In the future, we plan to incorporate multimodal information into SESTA and evaluate on more natural conversation datasets. We also plan to study performances on the online dialogue system, which has no access to the information of future. Thanks.